Hello everyone, we are going to go ahead and go through section 1.2, which is in your math journals, so your Algebra 2 math journals. I'm going to kind of walk you through some of the transformations that we're going to be learning about in this unit and kind of go through some example problems. I'm also going to have you create a chart or a table. So you're going to need some, whether it's line paper or just regular computer paper, you're going to need some of that available as well. All right, so here's what we're going to start with. We're going to start with horizontal translations and vertical translations. So I'm just going to highlight those. The big thing I want you to understand about horizontal translations, it literally translates into us talking about shifting a function left or right. So again, think about shifting it horizontally, left or right. A vertical translation is going to shift our function up or down. And so you can kind of read some of this stuff, and I don't know if this is going to make a lot of sense to you, but basically what they're trying to show you here is kind of how we can go ahead and work through some of our translations. And if you did that investigation, what we're trying to get at is kind of looking at some of our general equations. So for linear, our general equation kind of looks like this. And you'll notice that all of these equations are going to look very similar. So this is more of a linear one. Why is it linear? Well, because there's nothing squared. There's no, it kind of follows that format of y equals mx plus b. We also have, we could do absolute value. We could do quadratic. I could do cube root, I could do square root, I could do all different kinds of functions. We call this our general equation or our vertex form of our equation. And what I want us to get out of this is to understand kind of like what do these numbers, like the a value, the h value, the k value, what do they do to our equations? And that's what you guys were kind of exploring when you were doing the investigation. So if you looked at the investigation, you might have noticed that h, anytime you changed this h value, whether it was a linear, absolute value, quadratic, or cube root, square root, didn't matter. What happened is you shifted your function left or right. So with your horizontal translation, your h value is the one that makes a difference. And if you notice, there's already a minus sign here. So it's like x minus whatever h is. So like, for example, if I were going to shift my function left 3, okay, that means I want to shift it like towards the negative sign, right? So I want to go towards the negative side. I'm going to go ahead and move it left 3. So I'm going to go negative 3 would be my h value. Well, when I plug negative 3 into here, what this would change this to is x minus a negative 3, which then becomes x plus 3. So what it's going to look like when you look at an equation, it's almost going to look like it's the opposite. So when you see an equation, we'll kind of go over that in a minute, but when you see an equation, it's almost like if it says x plus 3, that means it's moving left 3. If it says x minus 3, it means it's moving to the right 3. And again, that's a little bit backwards because it kind of looks like, plus sign means we move right, left sign, minus sign would mean move left, but that's not the case in this one. And then the up and down, that's going to be your k value. So, and that's going to go as is. So if it's a plus a number, it's going to move it up. If it's minus a number, it's going to move it down. All right, so I'm going to walk you through a couple different examples, and we're going to do, I'm going to go ahead and start with like the linear ones and just kind of go through a couple different things with this one, just because those are the examples they show here anyway. So the first thing it asks us to do is talking about how we can move our function left or right. So if I wanted to move my function 4 units left, okay, what this means is if I had a function to begin with, okay, so let's say, I'm going to change this to, let's say I had f of x equals 3x. So that's my original function. If I'm moving it 4 units to the left, what this means is I am going to be moving, this is going to be becoming x minus, so remember it's your h value that's going to change, so it's x minus negative 4. Or in other words, x plus 4. So what I did is 4 units to the left, you're plugging in negative 4 in for h. That's that h value, or your original equation. So what I'm really doing here is plugging in negative 4 in for h. All right, so then how do we work this? Is we say, okay, if this is the transformation, this is what you're going to, in the function notation, what you're going to look at then is you're going to say, okay, I'm going to take, instead of, if this is my original, this one right here, instead of wherever I see x, I'm going to replace it with x plus 4. So my new equation, we're going to call that g of x, because that's the one after we translate it. We're going to get 3 times x plus 4. Because all I'm really doing is I'm replacing x in my equation with the quantity x plus 4. And so I can do a little, magic here with the distributive property, and I get a function of 3x plus 12. So what I notice now is that this original, and then now this one, this has now moved this function 4 units to the left. And what you can do is you can go ahead and graph that on your calculators to kind of verify that that's indeed what's happening here. So if you go to your y equals and you type in 3x, and then I'm going to arrow down, I'm going to type in, what was the other one? 3x plus 12. And you should see, whoops, I got some other stuff on my here. Okay, let me go ahead and turn that off. And I'm going to hit zoom 6, bring me back to kind of like a standard window. So there's 3x, and 3x plus 12 is over there. So what if you notice between the blue and the red line here is that literally you just shifted it 4 units to the left. And so that's going to be kind of how that transformation shows up. So you can always verify your answers graphically by using a calculator. All right, let's talk about a vertical translation. So let's talk about a translation of 6 units down. So let's say I give you an equation of f of x equals 2x plus 5. So that's our starting point. And we want to move that function 6 units down. So the transformation is we take this function, right? And it's our k value that's in. So I'm going to move it down 6. So really all I'm going to do is I'm going to subtract 6 from this function. So what this is going to look like is I'm going to have my new function, my g of x, is going to be my original function minus 6. So this is kind of your f of x, that's your original function, and now we're just going to translate it 6 units down. Again, we're just going to kind of combine like terms here. So now I have from my original function, which was this one right here, I went ahead and shifted it 6 units down, and I ended up with another linear function, but this time it's 2x minus 1. You might notice in both of those that the slopes never change. It's really just your y-intercept that's changing in all of those. All right, let's take a look at some more. Next, we're going to talk about reflections. So there are 2 different kinds of reflections. There are reflections in the x-axis, so I'm just going to kind of highlight this, and reflections in the y-axis. All right, so a reflection in the x-axis is what you're really doing is you're taking your entire function that you start with and you're multiplying it by a -1. So it's like a multiple on the outside of your function. So let's say if I started with a function f of x equals x plus 1, and I wanted to do a reflection over the x-axis. Okay, so that what I'm really doing is I'm taking -1 and I'm multiplying it by my function. So that's kind of like the process that you're doing. And so what this is going to result in, so my final answer, if I multiply -1 by x plus 1, what I get is -x minus 1. So this now, from here to here, if I have x plus 1, my reflection in the x-axis would result in -x minus 1. Again, you can go back to your calculators, and we can kind of show how that looks in here. So I'm going to put in x plus 1, and then I'm going to put in -x. Make sure you use the negative sign, not the minus. Minus 1, and that time obviously you use the minus sign. And I'm going to hit graph, and you should see how this reflects. So there's my original, and this would be a reflection in the x-axis. So remember, imagine like you're folding it along your x-axis. This part up here, this branch up here kind of gets, reflected over here, and this branch up here gets reflected down there. So again, it's just showing you a reflection. This is how we do it algebraically. This is how we look at it, graphically. A reflection in the y-axis is a little bit different. What they're really doing is, if you notice in here, they're not multiplying the entire function by -1, you're multiplying the inputs, or in other words, the x value by -1. So this is a reflection in the y-axis. So again, let's say I started with f of x equals 3x minus 6. So this is my starting. and I wanted to do a reflection in the y-axis. So what I'm actually doing is I'm taking my original function and I'm multiplying, or I'm changing that x value, that input value, I'm changing it to negative x. So what this is going to do, it's going to go 3 times, I'm basically replacing negative x in my equation wherever I see x. So it's going to look like that. So that means my final answer, my negative x equation, I'm going to get negative 3x minus 6. And so what you'll notice here is that the y-intercept didn't change, whereas obviously on this other one, the y-intercept did change. And obviously the slope did kind of go to the opposite side. So this would be a reflection in the y-axis. Again, what you're doing is you're multiplying the x's by negative, not the entire function, just the input value, so just that x value. All right, so now the fun part comes into play. We're going to talk about horizontal stretches and shrinks, and then we're going to talk about vertical stretches and shrinks. All right, so these I think are a little bit on the harder side, but again, what we have to kind of think about is both different types of functions. So for example, we're looking at a horizontal stretch or a horizontal shrink. Has to do with this, it's that a value out in front. So remember when I talked to you about the original functions, right? Those parent functions, those general equations. This a value controls kind of our stretching and shrinking. Another number, like if I put a number in front of this x, whether I put a 5 here or a 1/2 here, that's also going to affect kind of the stretching and shrinking of my graph. So what that's going to do, imagine you have a parabola, for example, right? So you have a parabola, let's say it looks like this, roughly. And then let's say if I stretch or shrink it, what might happen is that it becomes narrower or even wider. So that's what's going to happen with when we stretch or shrink our graph. So it's easy to kind of look at that a quadratic, absolute value type equation because they have the kind of symmetric, right? And so that's really what it's going to do. It's going to kind of pull our function. It's either going to make it kind of skinnier or wider, or if it's linear, it's going to get closer to the x-axis or closer to the y-axis, or in other words, further back. All right, so when we're talking about horizontal stretches and shrinks, horizontal is going to refer to that number on the inside. So whereas a vertical stretch or a vertical shrink is going to go ahead and multiply, like that's that a value on the outside. It's going to multiply the entire function by that number. A horizontal stretch or shrink is only going to affect the inputs. So there's a couple fun things you have to remember about this one. So if the a value that we're dealing with is greater than 1, the result is going to be a shrink. So a horizontal shrink. So remember, shrinking means that it's going to get, imagine horizontally that it's closer to the x-axis. So when your a value is greater than 1, it's pulling it this way. We're going to have, it's going to have a horizontal shrink. And then when your a value is less than 1 but greater than 0, we're going to have a horizontal stretch. Whoops, I spelled that wrong. So we're going to have a horizontal stretch. So again, this a value is the number being multiplied by your x kind of in the inside. So let's take an example. I think it's easier if we kind of look through some examples. So if I have f of x equals x plus 4, and I say I want to do a horizontal stretch, horizontal stretch by a factor of 2. So when we talk about this factor of 2, what that's telling you is what that, what that a value is. Now the catch here is with horizontal, it's not just, this is your a value, but when you put it in your equation, it has to be written as 1 over a. So what that means is if I'm going to do a horizontal stretch with a factor of 2, I am going to, the number that I'm actually multiplying by is actually going to be 1/2. So I'm going to take this original function and I'm going to multiply the inputs by 1/2. It's kind of the opposite, right? Or the reciprocal. And so if I do that, I get 1/2 x. So again, just replacing into this equation, all I'm doing is replacing it with 1/2 x plus 4. And so then my final equation is 1/2 x plus 4. And this was a horizontal stretch with a factor of 1/4. So why do they call it a horizontal stretch? Well, think about the slope of this line and the slope of this line. So this line has a slope of 1, right? And so when I have a slope of 1, that your line's going to be steeper. Well, if I have a slope of 1/2, it's not going to be as steep. So what happens to a linear equation when it's not as steep? It gets closer and closer to the x-axis. And so that's why they call it a stretch. It's stretching horizontally. In other words, it's getting closer to the x-axis. I'm going to go through one other example here. Let me grab a different pen. If I did a horizontal, we'll just say a horizontal shrink. And let's do a factor of 1/5. So I'll show you what that would do. So a horizontal shrink by a factor of 1/5. So basically what you're going to do is you're going to take your original function. Again, you're going to take the reciprocal of that. And you're going to kind of apply, instead of having, it's not really 1/5, it's 5x. So going back to our original function, I'll just use the one I used from before. I'm going to replace x with 5x, so I get 5x plus 4. So now, if I graphed this linear equation, and compared to my original one, this would be a horizontal shrink by 1/5. So again, let's take a minute to see what that looks like. This has a slope of 1. This has a slope of 5, which means that it's going to be steeper. So it's going to be further away from the x-axis. So when you have a horizontal shrink, it's going to be further away from the x-axis. If you have a horizontal stretch, it's going to be closer. And so what that looks like in linear functions is that means if it's a horizontal shrink, you're going to have a larger slope. And if you have a horizontal stretch, you're going to have a smaller slope. And obviously, if you're talking about quadratics or absolute value and other ones like that, you're going to have a little different looking graphs, but ultimately they're kind of the same general concept. All right, let me talk to you about vertical stretches and shrinks. So vertical stretches and shrinks. Okay, so this one actually I think is a little bit easier than the horizontal. So first and foremost, let's talk about the a value, because what this is going to be is the a value is being multiplied by your whole function this time. So it's not talking just about your input. You're basically taking a number and you're multiplying everything, the whole equation, by that number. So again, I want you to remember that when a is greater than 1, it's going to represent, so this is kind of the opposite, it's going to represent a stretch. So this is vertical, remember. And then when a is greater than 0, so I'm not talking about any negatives here, but less than 1, we're going to talk about a vertical shrink. So remember, vertical is up and down. So now we're talking about pulling it this way. And so we're stretching it this way or we're shrinking it this way. So now we're talking about how close it gets to the y-axis. So now we're kind of changing the way we're talking about this. So let me give you an example. So let's say I start with the function f of x equals 2x plus 2. And I want to do a vertical stretch. And we'll do by a factor, you'll see that a lot, of 5. Now the nice thing here is there is no, you don't have to do the reciprocal or anything like that. So only with the horizontal did you have to go ahead and take the reciprocal of this number here to be able to put it into your equation. So with vertical stretches and shrinks, it kind of stays the same. So really what you're doing is you're taking your original function and you're going to multiply it by 5. So how this is going to look is I'm going to have 5 times 2x plus 2. So I'm going to take that number 5 and I'm going to multiply by the entire function. So after I go ahead and do that transformation, I'm going to go ahead and distribute. I get 10x plus 10, my final answer. So compared to the original, if I graphed 2x plus 2 and now I graphed 10x plus 10, what you're going to notice is that it's going to be a vertical stretch by a factor of 5. Again, I want you to think about the slopes, rise over run. Linear. 2 over 1. If I stretch it 2 up and 1 out, that's going to be a lot further away from the y-axis than if I stretch it 10 up and only 1 out. So by increasing the slope by, a factor of 5, you're basically taking that linear equation and you're snugging it closer and closer and closer to that y-axis. We could also do a shrink. So I can show you an example of doing a vertical shrink. So we'll do vertical shrink by a factor of 2. So if I did that, a factor of 2, we'll kind of use the same equation. Let me see here. I get a vertical shrink by a factor of 2. All right, so what I'm going to do here, this one, you do have to take the reciprocal of it in order to get because it's a vertical shrink by a factor of 2. And so what's going to happen here is you want it to actually, in order to get it to kind of move away from the y-axis, you're going to have to multiply. So in other words, you're going to go ahead and take the original function and you're going to multiply it by a half. So it's a vertical shrink by a factor of 2, basically means that we're multiplying this by 1/2. And so what happens here is I'm going to get 1/2 times 2x plus 2. So then my equation would end up being, if I distributed, x plus 1. And so that's what I end up getting if I have a vertical shrink by a factor of 2. All right, the next thing I want to show you is just kind of a chart, if you will. And so this is where I'd like you to kind of grab a sheet of paper, maybe some line paper or just some regular computer paper. And I want us to kind of walk through a couple examples or also some just so that we have it all kind of clear. So these are all of our translations. And this is kind of my little, my cheat sheet here. So I started with the horizontal translations, that's the left and right. And I just kind of showed you in this box here that it is, what you do to your function is that you're either going f of x minus h, or you could do f of x plus h. And when you have the minus h here, it's actually moving to the right. And if you have the plus h, it's moving to the left. So that's just telling you how to move that function. And then I went ahead and did an example. So I started with this linear equation. I said I'm going to move it 2 units to the left. So that means basically what I'm doing is I'm saying x minus a negative 2, which ends up being f of x plus 2. And so then I go ahead and replace the x value in this equation with the x plus 2. And then I just wrote my final answers over here for these two. So this is my final answer for 2 units to the left. And then I did 2 units to the right, kind of similar concept. And I got g of x equals x. So again, this is just kind of highlighting what we talked about with horizontal translations. Vertical translations, very similar. Again, remember that it's up and down. That's going to be this k value. So when it's a plus k, it means it's moving up. If I have a minus k, it's moving down. So I just gave one example of each. So here's my original function. If I wanted to use it 2 units up, I would take my original function and I would add 2 to it. So here's my original function. I add 2. This is what I end up with. So that's what I got for my g of x equation. If I want 2 units down, again, same idea. Take your f of x equation, subtract 2 from it. I go ahead and do combine like terms, and I get a final answer of 5x minus 3. So those are your translations left, right, up and down for both horizontal and vertical. If you flip this over, these are going to just be my kind of my examples of reflection. So reflection, the x-axis. So when it's in the x-axis versus the y-axis. So remember, when it's in the x-axis, this negative is being multiplied by the entire function. So that's kind of like the rule, if you will. Here's an example. So if I give you f of x equals 6x plus 1, I'm multiplying if I want to do a reflection in the x-axis, I multiply the entire function by negative 1. So you do have to distribute it to both. And so I end up with an answer of g of x equals negative 6x minus 1. If I wanted to do a reflection in the y-axis, remember that's just going to be multiplying my x values or my inputs by negative 1. So if I take a look at my rule here, all I'm really doing is replacing x with negative x. And so your y-intercept doesn't change. So notice when you do a reflection in the y-axis, my y-intercept doesn't change. So it still is negative 1. And so the only thing that really changes is that slope, right? So I get negative x minus 1. And then the shrink, the horizontal stretch and shrink is what we just kind of talked about. But again, I think this is probably the harder of all of the transformations. So again, horizontal stretch and shrink, if I have horizontal means that I'm just kind of, my A value has to do with the input, so I'm multiplying by A. So if it's a stretch, it is, A is between 1 and 0. If it's a shrink, it's greater than 1. And remember, 1 over A is the factor. So again, here's an example. 3x plus 1 is my linear equation. I said I'll stretch by a factor of 6. So that means what I'm going to plug in there is 1/6 for my A value because it's that reciprocal. And so 3 times 1/6 x plus 1, and I just get x plus 1. If I did a shrink factor of 1/5, so again, the A value then would be the reciprocal, which is 5. And so I'm going to multiply, I'm going to go ahead and multiply the 5 by everything in here. So I get 15x plus 5. And then for vertical stretch and shrink, I have my A values being multiplied by the entire function. And I have a stretch value as my A value is greater than 1. My shrink is A is less than 1 but greater than 0. And A is my factor. And I think I misspoke on the other page. So this one you do not have to do a reciprocal. I think when I did the example on the other one, I told you right here that has a vertical shrink by a factor of 2. I think what I needed to do here is change that to a 1/2. I should have made a reciprocal on that one. So I'll go back and edit that on your notes if you would, please. All right, so anyway, here's your example. It says f of x is 1/2 x plus 1. I'm going to stretch it by a factor of 4. So all you're really doing is multiplying 4 by the entire function. So I get 2x plus 4. And then if I have a shrink by a factor of 1/6, so again, there is no reciprocal. I misspoke on the other one. You're multiplying 1/6 by the entire function. I get an answer of 1/12 x plus 1/6. All right, so that's kind of the table, and that way you can kind of use that as you're kind of going through and hopefully help you make some sense of some of this stuff. Let's go through a few examples before we're done here, and then you guys can practice on your own. All right, so for the first one, it says we're going to write a function g whose graph represents the indicated transformation of the graph of f. Use a graphing calculator to check your answers. All right, so we want to do a translations of 2 units to the left. So remember, that's that h value. So what we're really doing is we're taking our original function, and since we're going to the left, that's going to be, it's actually going to cause that to be an x plus 2. Remember, because moving it to the left, it's like saying x minus a negative 2, which causes that to be x plus 2. So then if I go ahead and plug x plus 2 to this equation in place of x, I get absolute value of 1/3 x plus 2. And so I get an answer of, and I'll go ahead and write it as a g of x equation. So I get g of x is going to equal absolute value of 1/3 x plus 2/3. The next one says a translation of 6 units down. So again, what you're doing here is you're taking your original function, and that's that k value on the end. You're just going to subtract 6 from it. So if I take my original function, so negative absolute value of x plus 9 minus 1, and now I'm going to subtract 6. So just be careful that you're not, like, this is not distributive property here. These absolute value symbols need to kind of stay where they are. So what this results in is a negative x plus 9, and then basically the only thing I can combine together is this -1 and the -6 to get -7. The next example says a translation of 7 units down. So again, all I'm really doing here is I'm subtracting 7 from that. So if I take my original function and then I subtract 7, my g of x equation would result in -2x minus 5. All right, let's try a couple harder ones. I think there's some harder ones on the next page. All right, so this one says 1/2 x plus 8 is the function, and we're asking to do a reflection in the x-axis. So remember, a reflection in the x-axis means we multiply the entire function by -1. So all you're really going to do here is take -1 and multiply by 1/2 x plus 8, And what you get for an answer would be, I get negative 1/2 x minus 8. All right, reflection in the y-axis. So then what that one does is it changes my inputs. So I'm going to have just my x values are going to be affected here. So how this looks is I'm going to have 4 plus, I'm going to have negative x plus 1, basically is what that's going to turn into. So one of the things that I noticed, and this is just more of a housekeeping type thing, but when you have an absolute value with the variable term negative, what they want us to do, kind of like think about factor out that negative 1. And so what that does is it allows us to have that negative value kind of treated differently, right? So that all we're really doing is we're taking out that negative 1. If you remember what the definition of what absolute value means, it means distance from 0. And so when I factor out this negative 1, I can kind of take the absolute value of negative 1 separately from the rest of the function. What happens here is if I take the absolute value of negative 1, I get 1. So ultimately, by factoring out that absolute value of negative 1, it really doesn't change my function any. So what I get for my final answer is I get 4 plus absolute value of x minus 1. And so this becomes my final answer. And again, the only thing I did here was kind of I took out that negative 1 out of here so that I could go ahead and kind of reduce that down a little bit more. All right, number 6, vertical shrink with a factor of 1/5. So a vertical shrink with a factor of 1/5 means that we are going to go ahead and do 1/5 times my original function. So remember, the vertical is the one where you're multiplying the outside. So I'm going to take 1/5 and I'm going to multiply it by my original function, which is negative 5x, and I'm going to get negative x. So my final answer is g of x equals negative x. All right, a vertical stretch by a factor of 4. So again, what we're going to do is take 4, we're going to multiply it by the entire function. So I'm going to take 4 and I'm going to multiply it by absolute value of x plus 3 plus 2. Now be careful here, you're multiplying this 4 by the entire function. So it's not just the absolute value sign. So when you simplify this, you're not distributing this throughout the absolute value. So what this becomes is just, oops, let me grab a pen. What this becomes is just g of x equals 4, absolute value of x plus 3. But then I do have to distribute to this 2 here. So I get plus 8 on that side. So just be careful on that one, that you're remembering. You can't really think of these as parentheses, those value symbols, but you're still multiplying those two quantities together. But you have to write it as 4 times, absolute value of x plus 3. You can't distribute it. All right, a couple more. So we have a horizontal stretch by a factor of 6. So remember, this is the one that you have to take the reciprocal of, and you're changing your outputs. I'm sorry, your inputs. You're multiplying by 1/6. So it's a factor of 6, so the a value is 1/6. So basically what you're going to do is you're going to plug in 1/6 x into your equation wherever you see x. So you're just replacing x in your x equation with 1/6 x. And so if I do the math here, I get 3 times 1/6 is 1/2. And it doesn't really affect my y-intercept at all, so I just have that kind of staying the same. Next one, horizontal shrink by a factor of 1/4. So what that means, again, take the reciprocal, you're going to change your inputs, you're going to multiply by 4. So 4 times, whoops, we're going to do, we're going to multiply, we're going to replace the x with 4x. And so what I get is a negative on the outside, but then I have 8 times 4x, which is 32x. So the absolute value of 32x minus 4. And the last couple says, I'm giving you a function, I'm just giving you a basic parent function of absolute value. Write the function whose graph represents a reflection in the x-axis. So that would be negative. So basically what you're doing is you're multiplying by -1. What's the next part? A horizontal stretch by a factor of 3. So a horizontal stretch by a factor of 3 means that we have the negative, but then we're also going to multiply the inputs by 3. And then we're going to have a translation of 5 units down. So here's reflection, here's the horizontal stretch by a factor of 3, and now we're going to have a translation of 5 units down. So to do all 3 of those transformations to this function. And so what that would look like is I'd have the negative out in front. I'd have 3x instead of x inside there. Whoops, I should have put a 1/3 here because it's reciprocal. So 1/3 x, change that. And then I would have the -5 on the outside to represent the shift down. So from our original parent function to my new function, that has 3 different transformations going on there. The last one says, which of the transformations in section 1.2 will not change the y-intercept? And so we talked about this one here, the horizontal stretching and shrinking. So like if you look at the horizontal stretch, remember how we had the y-intercept of -9, still had a y-intercept of -9. So it's the horizontal stretch and shrink. All right, so I walked kind of through a whole bunch of different examples. I would encourage you, you're always welcome to obviously go back in the book and look through some of the examples there. They could be a little bit different. Feel free to watch the video again if you kind of pause the parts. I would write down any questions or highlight any things on here that you would like me to go over in class. And so when I see you in this class, we can kind of go over anything that maybe you had issues with or needed clarification on. If you're completely lost, have some really big issues, email me, and maybe we can set something up where we can meet and go over some of this stuff. All right, have a great day.